Have you ever wondered how you teach a robot to do, well, anything complex? Now imagine this. What if you had to teach a million of them, all at the same time? Today, we are going to pull back the curtain on the incredible virtual pipeline Nvidia has built to train the next generation of physical AI. It all kicks off with this vision that honestly sounds like it's straight out of a sci-fi movie. Everything that moves will be autonomous. Just take a second to let that sink in. We're talking cars, factory arms, you name it. Every machine just operating on its own. A vision that big, well, it brings with it a technical challenge that's just as massive. And that really brings us to the core of the problem, right? How in the world do you give a machine a lifetime of experience so it can actually interact with the physical world? I mean, look, training a chatbot on text from the internet, that's one thing. But teaching a robot about physical action, about control, about the pure chaos of reality, that is a whole different ballgame. So here's the game plan for today. We're going to start with the single biggest bottleneck holding robotics back. Then we'll see how they build an entire universe of ritual data, put the AI through a kind of digital boot camp, and then bridge that tricky gap back to the real world. And finally, we'll get to meet the AI brain itself, Groot, and talk about what this all means for the future of AI that can actually move around. All right, so let's dive into the biggest hurdle in pretty much all of robotics, what's known as the data bottleneck. Okay, here's the heart of the issue. An AI, like a chatbot, it learns from the internet, right? It's got this bottomless library of text and images. But a robot, it needs to learn from physical experience. It needs what we call action and control data, which basically means recording endless real-world interactions. And that process is painfully slow, it's incredibly expensive, and it's basically impossible to do at the scale you need. So if you can't get enough data from the real world, what do? Simple. You build a digital foundry to create your own. This is where the whole solution really starts to take shape. Now, at the heart of this data factory are two incredibly powerful platforms, Nvidia Omniverse and Cosmos. You can think of these as the tools that let developers build, from scratch, basically infinite amounts of diverse and photorealistic training data. And the stuff they create is called synthetic data. It's exactly what it sounds like. Data that's artificially generated, but it perfectly mimics real-world physics and visuals. This right here is the breakthrough. It completely shatters that data bottleneck we were just talking about, because now you can create a virtually limitless number of training scenarios. The process itself is just ingenious. First, you start by aggregating a small sample of real-world data inside Omniverse. Then Cosmos comes in and acts like a multiplier. It takes that one little sample and explodes it into these massive volumes of diverse, photorealistic data. It can change the lighting, the textures, the object positions, endlessly really, to get the AI ready for any scenario you can imagine. Okay, so we've got the data, an ocean of it. Now the robots need a place to train. So welcome to the virtual gym. And that training ground is Nvidia Isaac Lab. Think of it as a simulated world where these AI models can practice super complex tasks over and over and over again. They get to learn all these new skills in a perfectly safe and controlled environment. It's basically where the robot AI goes to school. Inside Isaac Lab, they're mainly using two training methods. First, there's imitation learning, where the AI just learns by copying behaviors it's shown. Super straightforward. And then there's reinforcement learning, where it learns by trial and error. It gets little rewards for doing things right, kind of like how you'd teach a dog a new trick. But, practicing in a perfectly clean lab is one thing. The real world is messy, it's unpredictable, so this next step, the final rehearsal, this is all about making sure the skills learned in the simulation are actually going to work out there. This is, you could argue, the single most critical challenge in all of this, bridging what's called the sim-to-real gap. You have to test these new AI models like crazy to make sure they're tough enough for the unpredictable dynamics of the real world. And to bridge that gap, they use this really powerful toolkit. They run tests in a digital twin that has perfect real-world physics. They use a technique called domain randomization, which is a fancy way of saying they just add chaos to the simulation, randomly changing the lighting, textures, even friction. Plus, they use high-fidelity sensor simulation, so the robot's virtual eyes see the world exactly like its real cameras would. And it gets even more complicated, because real-world places like factories often have whole fleets of robots. That's where Nvidia Mega comes in. It's a platform for testing dozens, even hundreds of robots at scale, making sure they can all work together as one big coordinated team. So after all that data generation, all that training and all that testing, what do you actually get? Well, you get the brain, the final product of this entire pipeline. So, meet Groot. This is a generalist foundation model for humanoid robots, and it is the direct result of all that intense learning in simulation. This isn't an AI that's built for just one single task. It's designed from the ground up to be a versatile, general-purpose brain. What's really brilliant about it is how its design is inspired by human thinking. See, Groot has this dual system. It has a slow thinking part that looks at the world, reasons about what it should do, and then makes a plan. And then a fast-thinking system kicks in, translating that high-level plan into the precise, fluid, real-time movements of the robot. So let's just zoom out for a second and see how this all comes together to create this continuous loop for building smarter and smarter robots. You can really simplify the entire pipeline down to a 3-computer system. Computer 1 is the data factory, generating all that synthetic data. Computer 2 is the virtual gym, training the AI in simulation. And Computer 3 is the AI brain, Groot, running inside the physical robot out in the real world. And the ultimate goal, the big payoff for all this incredible work, is one word: generalization. The point isn't just to make a robot that does one thing really well. It's to create robots that can manipulate everyday objects and carry out complex, multi-step tasks, adapting to new challenges as they go. It's a truly remarkable system. And it kind of leaves us with this pretty fascinating final thought, doesn't it? If robots can now learn and master incredibly complex physical skills in a virtual world practically overnight, what does that mean for our own future and for our relationship with these machines as they get more and more capable? Thanks for joining us.